Okay, guys, let me share the lab procedure introduction. So this is what you have there here inside your iCollege. Now I'm interested to know what really is a VSPER stands for, and that's what I promised to tell you what VSPER stands for. Well, let's look at this first here. I'll make a space here. And okay, guys. So VSPER stands for V for valence. S for shell. E for electron. P for pair. And R for repulsion. So this is valence, shell, electron pair repulsion procedure or method. So what is really is used for? It's used for determination of a shape of a molecule. Now, why is this very important? Well, it turns out to be the shape of a molecule is very, very important, especially if you are working in the pharmacy or anything related to drug industry. Some chemotherapy will be using some special chemical organic compound that can chelate, can encapsulate the tumors and let them in one location. It will not let them move freely. So it encapsulates like a scissor, like a fish crab. So it's really encapsulates the tumor, preventing these tumors from escaping into the blood stream. So not spread all over and attack all the cells, healthy body cells. So you need to design a compound that really can do that. So VSPER will give you the opportunity to learn about those type of chemicals. The same thing is purification of tap water. You need some chemicals that really encapsulates inside the tap water. You have a lot of bacteria. You have some viruses inside tap water in the old rivers, whatever they dump inside the rivers. You have some viruses, E. coli, whatever you name it. So in order to have inside tap water some chemicals that's really targeting those bacteria or viruses or whatever contaminations they are present. So you need some special chemicals to do that. So the design of those such chemicals will really force you to know about the shape of a molecule you are looking for for application. Okay, guys, this is the importance of VSPER. Now, what really is the whole VSPER is really based on the Lewis dot structure. With the help of Lewis dot structure, is we can see that's all the Lewis dot structure will give us all the orientation of the valence electrons of each atom in space, correct? And the covalent bonding between adjacent atoms, correct? So with this knowledge, we can see that the repulsion, the electron pair repulsion, whether they are bonding or non-bonding, they are negative particles, correct? They start repelling each other. Negative near negative, they repel each other. So this repulsion here will continue until the molecule come to the, to state of stability. The molecule will be stable, will start to stabilize itself by having a shape that's minimizing the repulsion between those electrons, valence electrons. Are you following me here? So there will be repulsion will come to the point that will be in space. Those are far away from each other. So they are with the minimum of repulsion, because they are two negative particles, one electron, they will not attract themselves. They will repel each other. So that's what is minimizing the repulsion will lead to the very stabilized shape of the molecule. And that's the whole about VSPER. And that will not be easy unless we know how to do to draw Lewis dot structure. So before we are going to VSPER, we have to see how we can get the Lewis dot structure straightened out and then draw it. So let me here come and then look at the examples I gave you here. You can read the rest of this, but I give you example here of the whole thing here. So I give you all this stuff here and all the code, but I am interested to know of this one here. Look at carbon dioxide. That's the molecule. So here it is. Let me share it. I might have to stop sharing here and then share the new one. Yeah, still sharing the same one. Okay, so this one here and this one here. Okay, guys, so look at this. What's happened is Lewis dot structure does have certain rules to be used. What are those? First of all, we have something to introduce ourselves and Lewis dot structure. Of course, first of all, everything here is to know that electrons are represented by a dot. Each electron is represented by a dot, correct? That's Lewis dot structure. So that's what we have. That's each electron is represented by a dot. Second, we have to know that electronegativity is very important. We keep the least electronegative atom at the heart of a molecule. And the electronegativity, we might have not covered this one here yet in the lecture, but you will learn that electronegativity is the ability of an atom to pull out valence electrons within a chemical compound. So if I have, for example, if I have fluorine here and hydrogen here, this one has 7 valence electrons. So we just go back here. So here it is, hydrogen and fluorine. It has 7. That's 7. This one has 1, correct? So in order to get a bonding between hydrogen and fluorine, so this is the bond between them, correct? Can you see it, guys? Can you see it? Okay, so this one here, it tells you, this one we don't have a central atom. There is central atom, you have to have 3 atoms and more. To visualize what central atom is, means the core and the heart of the molecule. Here you have 2 atoms, you cannot start saying that you have central atom. Central atom, you have to have 3 atoms or more. So if I look at this one here, for example, this example here, this one called boron trifluoride. If I look at the boron trifluoride, boron has 3 valence electron in group 3 or 13, 3A or 13. It has 3 valence electrons. And fluorine in 7A group or 17, it has 7. So here is 6, and here is 1 here. Correct? 6, and here is 1. Here's 6, and here is 1. So we have 4 atoms. Then we'll have what? Central atom. The central atom is the atom that has the least what? Least electronegativity. It can't pull electrons from the adjacent atom. So fluorine is the highest electronegative atom in periodic table, and francium and francium and cesium may be the last or the least electronegative. So they can't pull. The metals can't pull. The metal can give away their valence electrons. The non-metal can pull electrons to itself, can gain those valence electrons. So with this fact, I can tell you about the electronegativity. I will mention that in the class. That's a scientific joke, but it's not really a joke. That's a real. So let me just tell you, if you at the times two people, they have issues about the life insurance, and somebody wants to do damage of the other spouse. So what the other one has a little bit of knowledge of chemistry. So bought about a couple thousands of toothpaste and empty them in a big container and let them boil, cook very slow under very slow temperature, evaporate most of the H2O inside. What's happened inside the toothpaste, you have calcium fluoride. That person in the family wants to have fluoride to be very highly concentrated. And he or she knew that the fluorine atom has the ability to pull out anything, any valence electrons out of, out in the neighborhood of the chemical bonding. So then when everything, he cooled down the whole toothpaste here, picture here, and then fill one of those by one and then put it there. The other spouse came the second day, start brushing the teeth. And then one tooth after the other is falling down. That spouse who had really brushed the teeth came out to be, looking like a 100-year-old person with no single tooth inside the mouth. Now, this is a problem. What's happened? Well, it turns out to be the fluoride inside this toothpaste is so highly concentrated, the fluoride ion, and the fluoride ion has the ability to pull out the valence electrons of the gum structure. The gum structure is made of carbon, nitrogen, whatever other compounds there. They have valence electrons. Their valence electrons are pulled by the fluoride, and that's the reason we add fluoride in the toothpaste to kill the bacteria. It does attack the bacteria. It pulls out the valence electron from the bacteria itself, so the bacteria dies. The bacteria die out, and that's the whole idea, to add fluoride inside the toothpaste, but in small amount. If you add too much of it, like the person did, then you can cause a lot of damage. Are you following me here? So the fluorine atom or ion, they have the ability to pull out those electrons from adjacent atoms in a chemical compound. Are you following me here? Everybody's following? So with this type of thinking, we cannot do Lewis dot structure with two very strong electronegative. They'll start fighting themselves. When I say to death, really to death, and then those molecules start what? Somebody will tell me what happens if you put those two electronegative atoms near to death, means they start explode. They start explosion. You'll hear a big pop and a lot of damage. Are you following me here? So if I put the first one, fluorine here, whatever it is, those are more electronegative, or oxygen, that's called peroxide. They're not stable. You have to put them inside the fridge. If the heat is just enough, they'll start popping up. not stable, because they fight each other. Each one wants to pull out the valence electron toward itself, and the other atom will do the same. The other atom will do the same thing, and then you have the molecule being really decomposed under a big explosion. Are you following me here? So that's what we mean by electronegativity. So now look at this one here. You think this one is like looking like this? Now, the fluorine atom is so aggressive, it will pull out. So this here will be looking like this. Maybe get another color here, show you. Here it is. The molecule will be looking. So hydrogen looks like does not feel, see here far away, does not feel its valence electron. Hydrogen has no power on controlling its valence electron. This valence electrons is pulled towards fluorine. So this valence electrons here is pulled this way towards fluorine. So hydrogen feels I'm losing my valence electron. I don't have it. So it resides more towards fluorine. So therefore, this one will appear positive, is losing. This one will appear negative, is gaining this partially negative. So this looks like ionic compound, but made not of metal or non-metal, made of two non-metal atoms. But one is so electronegative, so aggressive, it will pull electrons. There will be no equal distribution of valence electrons. So covalent bonding is between combination between two or more nonmetals. You know, they share those valence electrons. But in this case here, no sharing. That's partial sharing here, not full sharing. So that's partial sharing. Okay, guys, so, and that's what happened in the electronegative atom. We have to say that because we have to know that this is not good to keep this electronegative in the heart of the molecule. You get a lot of problems with that. Nature will not support that. And if you try to make a molecule like this, it will be not stable. It will decompose, correct? So now let's look at this here. Let's go back and look at the whole thing here. We have carbon dioxide, the first one. So the first one here. Carbon dioxide here, guys. It has carbon. It has 4. And oxygen it has 6. So 2, 2, 2, 2, 2, 2. And I'll make this 2 out here. Maybe so I'll put this one here out. Oops. Okay, guys, here it is. So this one here, carbon is here, has 2. Oxygen has 2. And 6 here. And carbon here has 2, 2. So here it is 2. Now you will see that carbon is the least electronegative. Fluorine is the first, and followed by oxygen. Hydrogen is the second highest electronegative. So now what will happen here if I have they'll start connecting to make a double bond. And each carbon oxygen, they have to have 8 valence electron, shared or non-shared, bonding or non-bonding. If you look at oxygen, you count them 1, 2, 3, 4, 5, 6, 7, 8. This one is obeying the octet rule. Good. How about carbon? Carbon is 1, 2, 3, 4, 5, 6, 7, 8. So carbon is 8. But in case of oxygen, it has 2 sets of bonding and 2 sets of non-bonding. This is called non-bonding. Those called what? Non-bonding. Well, it's not allowing us to draw very well, but anyway, so here it is. So we made them double bond because it's to obey the octet rule for oxygen and carbon. Both of them are 8. Now, this is the central atom. This central atom, I'll give it the designation of A. And this is the terminal atom or at edge atom here called B. Okay, guys, so this here, the VSPER code for this molecule is AB2. AB2. And then I go to the I go to the table to look what's AB2 code. What will be the shape if I have AB2? No lone pair. So it looks like it will tell you the shape is linear. And the angle of the linear is 180 degrees. And the question is, it is polar or non-polar? Well, there is polarity because polarity is the difference between electronegativity, correct? This is about 3.5 electronegative, correct? This one about 2.5 or something like this. So, and you look, it's polar, correct? It's covalent polar, but it's not, the whole molecule is not, but the bonding itself from here will be pulled this way. That's the beginning of the pulling. And from here, this way. So when the two dipoles, this is called dipole. And here called dipole. They have the same strength, opposite direction. So they cancel themselves out. They cancel themselves out. And therefore, carbon dioxide, although it has two polar bonding within the molecule, but the whole molecule is non-polar because of the fact that those two dipoles are canceling themselves out. So we can expect this one here to be non-polar. And moreover, you can say all the time, if this B here, the terminal are similar, then you can expect the molecule to be what? Non-polar. To be what? To be non-polar. So let's take the other one. Now here we have boron trifluoride. We said now fluorine is the most electronegative atom. Please stay aware. Always we keep the most electronegative atom at the edge. We can't put it in between. We can't. They will start fighting each other and the molecule not stable. So this is the best orientation in space, minimizing the repulsion between those valence electrons, correct? So it turns out to be, let me see here. Let's get the code. Let's get the code here. This is central atom A. This is B, B, B. So this is A, B, 3. This is the VSPER code called AP3. And therefore, because it's AB3, we can expect this one here to be looking it up. You have to look at the table there. Bring this one here for the quiz and the midterm. Trigonal planar. So from the code, we have central atom A, three terminals or at the edge, AB3, no lone pair on the central atom. So trigonal planar. The trigonal planar will give you, this is 120 degrees. Okay, guys, how much is it? 120 degrees. Now, it is polar or non-polar. Since they are the same atoms here, the dipoles will be going this way. The other dipoles will get this way. The other dipole will be this way. Because fluorine is the most, always the direction of the dipole, always towards the most electronegative atom. Okay, guys? So, and if you look at this, because they are similar, what we can say, polar or non-polar? Non-polar, perfect, non-polar. Non-polar. So let's take the fourth one. Okay, let's take the fourth one. Okay. The fourth one here, the same thing. Let's make, this is chlorine is 3.0, carbon is 2.5. So you can see that the chlorine is more, atom is more electronegative. So the whole dipoles are going going will be this direction towards the so it will be always this way, correct? Starting from here down, starting from here the other side, starting from here to the other side, from here to the other side. So it looks like they will cancel themselves out because it's the same strength, the same electronegativity difference. So they'll start pulling themselves out. So they cancel themselves out. So this one here is polar. What you say, non-polar or polar? Because they are similar, correct? Those are similar. So expect the electronegativity difference, which is polarity, will be the same, but they are different directions. So will be, this one will be non-polar. Now, what is about the code? What's about the code? Well, it turns out to be, this is our A, this is a B, this is a B, this is a B, this is a B. This is, the code is AB4. The code is AB4. So you'll memorize it. It's just small tiny tables. Not AB4 is, the shape is tetrahedral, and the angle of this tetrahedral is 109.5 degrees. Okay? And it's non-polar because you have similar terminals. Correct, guys? So we went to AB, no central atom. That's linear, 120 degrees. Depending on the atoms, the difference in atoms can be polar, can be non-polar, correct? We went to AB3. We said is trigonal planar. If the atoms are equal, they will be non-polar, and the angle is 120. We went to AB4, correct? If the atoms are the same, so there will be non-polar, and the shape of the molecule tetrahedral. Now, if I change one of those here, okay, it still be, but if I change it to, say here, I change it to fluorine. If it's changed to fluorine, what will happen? Now it will turn out to be what? Everything the same, but the polarity will be what? Will be polar, correct? Because they are not the same. 3 are chlorine and 1 fluorine. There is a difference. They will be polar. This molecule with 3 chlorine atoms and 1 fluorine is polar, correct? Because there will be a difference in the electronegativity. With this one here, that will lead to polarity. That will lead to what? Polarity. The shape here will not change. AB4. Regardless, whatever you have, fluorine, whatever the atom is, you look at the group, whatever is any atom can be a group, correct? That's a group. Now we have to look at the zones. The zone or the unit are number of single bond or triple bond or lone pairs. So here, how many how many units or groups or zones? 1 and 2. We have 2 sets of double bonds, so we have 2, correct? How about here? 1 single bond, second single bond, third. We have 3 regions or zones. Okay. So, and here how many? 1, 2, 3, 4 single bonds. 4 single bonds means we have 4 zones, 4 regions. Okay, guys, let's do the last one here. Let's do the last one, and then we'll do our lab. We'll do our lab. So, the last one here is, now it's a little bit different because the fact is now we have a lone pair here, correct? So we have to watch for the lone pair here, guys. We have to watch for the lone pair. So we have A, that's the least, correct? Oxygen is the second largest electronegative, B. However, now we have something here, lone pair, we call it E. How many of them is 1? How many of them is 1? So I have the code of A, B. How many B's I have? 2. Regardless whether it's oxygen, whatever but I have a group here attached to the central atom. And then I have E1, one lone pair. So I look at the shape of this. Shape of this will be AB2, will be bent. Will be what? The shape of this, the molecular shape will be bent. And the angle, because of this one is 1 here, it looks like a 3 because it has 3 zones, correct? How many zones is 3? One single, one double bond, second double bond, and 1 lone pair. So 3 zones. Why? 2 sets of double bond and 1 lone pair, so 3. Always, whenever you look at the zones, you just add those here, correct? Here I have CL4, correct? This example here. I have AB4. So how many I have here? 4. 4 zones, correct? You just look at the B. If you have an E, you have to add it up as well. So AB2 is bent, P and T, bent, correct? So this bent here, because it has 3 zones, we know the 3 zone without lone pair is around 120 degrees, correct? Triangular planar without the one we just did, which is BF3, correct? That's A, B3. And it's trigonal 120. 3 zones, same. This is 3 zone as well. However, because of the lone pair will suppress, will be less, will be this one here, will be less than 120 degrees. So maybe around 118 degrees or so, correct? Because we have a lone pair. Now, polarity of this, blindly, without looking, just like this, central atom has a lone pair, it has to be what? Polar. As we said, blindly here, if the atoms terminals are the same, has been non-polar. This one here is because of this lone pair here. So this one here is polar because of the lone pair E. Okay, because of the lone pair, it has to be polar. Anytime I have Lewis that structure that has a central atom that has a lone pair means orphan valence electron. They are not participating in any bonding. They are non-bonding or orphans. Okay, they are orphan. They are non-bonding. They're standing by themselves alone. They are not participating in any type of bonding. Correct, guys? So This is this, and the last one maybe H2O and ammonia. So, and then we'll do ours. So ammonia, H2O first. Let's do for me the code. So we kept the hydrogen always will be terminal. Hydrogen has one electron, cannot be in the middle. So always hydrogen here is a terminal atom, always for hydrogen. So here it is. This is A. This is, this is A. And this is B. And this is B. This is E1. This is E2. So the code of this A, B2, and E2. Okay, guys, A, B2, E2. The code is A, B2, E2. We have two lone pairs, two terminals, and one central atom. This is A here. And this is B. So with this here, because we have two, the more we have lone pair, the more suppression of the angle. So we can expect this one here. We have 4. Remember the 4? We have CCl4. I did not tell you tetrahedral. It has 109.5 degrees, correct? Well, you have two lone pairs, so I can expect this one here will be suppressed. This is 109. That's two suppression here. I have two of them, so the angle will be 105 degrees. It's suppressed by the two. So this is AB4, correct? I have 4 zones. 4 zones here. Here I have 4 zones because you have to have those up here. I have 4 zones as well. But because of the lone pair, the angle is suppressed. It is polar or non-polar? Polar, correct? Why? It is polar. Why? Yes. And it has two E's. Okay, so the more lone pair you have on the central atom, the more polar the compound, correct? And the smaller the angle, the smaller the angle. So we went from 109. Now we will see the ammonia here. We'll go even further. Ammonia is how many zones? 1 zone, 2, 3, and 1 lone pair here, 4. Ammonia is 107 degrees. See, 1 lone pair, just 1 lone pair ammonia. Although it has 4 zones, so 4 zones. Ammonia has four zones, H2O has 4 zones, and CSCl4 4 zones. All those 4 zones. Now the CSCl4 no lone pair, the angle is larger, 109.5. You have 1 lone pair, the angle is 107. You have 2 lone pairs, the angle is 105. Now suppose I have a central atom that has 3 lone pair sets. So what do you think the angle will be? Will be less than 105, maybe 103, 102, correct? So the more lone pair on the central atom, the least, the smaller the angle is. So now for ammonia, let's look at the ammonia here. Can I take this one out? Take it out? Okay, so I'll take it out. Then we'll look at this. Ammonia is, let's look at the ammonia here. The code of ammonia here is, I have 4 zones, correct? 1, 2, 3, 4. 1 lone pair set is, we treat them as one equally, so as a zone or a region. So then we have, this is B, terminal B, this is B, and the lone pair here is E. So this is A, this is A here, our A here. So A, B3, A, B3, E1. This is 4 zone, but it has one single set of lone pair, correct? It has one single, so this will be the other, this one here, we did not say this one will be bent, by the way. So bent, if you have A, B2, E2, that will be, the shape will be bent. Here, the shape will not be bent. Oops, sorry. The shape will be called trigonal pyramidal. This is trigonal pyramidal. So trigonal pyramidal, you have A, B3, E1, 4 zones. And the angle is 107. H2O 100 is 5 because that's 2. Suppress more. This is the angle here is 105 degrees. So polar, yes, polar. Why is polar? Because of what? Lone pair. Now, which is polar, H2O or ammonia? I just say it. So which one has central atoms that have more lone pairs? Oxygen. Oxygen has 2 sets. Oxygen has 2 sets. Here one, here one. 2. The nitrogen has only 1 set. So I can expect H2O is more polar than ammonia. That's true. That's true. Any question you have? Okay, so now we did all the stuff here as a practice. Now let's do our actual lab. You can make a note after me, or you just look at the video then later on. So let's look at the H2S. What is the structure? So if you can't draw it per hand, what I suggest you go to the website and Google the shape of, the Lewis dot structure of H2S, and then just put it here inside the. So I don't mind, just look at it. The main thing is you know how the structure of it. So just put it here inside from the website. Just put it here, correct? Just Google the shapes, all those shapes, and then put the shape inside and paste them inside. And the other stuff you can type. Everything you can type. That's Microsoft Word. You can type the information. So now this is without looking at the website to look at the shape. We can determine the shape, correct? So let's look at the shape here of this H2S. So what's the name of H2S? Dihydrogen sulfide, correct? Dihydrogen sulfide, according to the covalent nomenclature. So the hydrogen always terminal. That's our saying, always hydrogen will be terminal. So terminal. And the sulfur with 6 here, valence electron. This is 1. And this is 1 here. So it will not allow me to draw. So 1 here for sulfur, 1 for hydrogen. So it looks like this. So this is the Lewis dot structure, because sulfur is the 6A or 16 group, is always will be in the middle, because hydrogen is always terminal, cannot be in the middle. So therefore we can see the code. Let's look at the code here. This is my A, this is my B, this is my B, this is E, and this is E. So this is the code is, the VSPER code here will be A, B, 2, E, 2, correct? That's the code. I go and look at the table, A, B2, E2, what will be? Bent, correct? The shape is bent. And the angle is less than 100 what? This is 2 lone pairs, correct? So I'm expecting like H2O will be around what? 105 or something like this, around. So around that like H2O. So bent H2O is polar or non-polar? Polar, because lone pair E. That's the first one. And the angle is around 105. So we filled all the stuff here you have. You just go and write your notes, and then when you feel you can type those in. You can type everything except the Lewis dot structure. It's very hard to type and draw, so you can just Google the structure of it, which will be like the same like ours, and put it just here inside. Minimize the image and then squeeze it inside. So this is the first one. Now, this is the theoretical stuff. Let's do now, see how does it look like with, remember, as hydrogen is a very small, tiny one. With this one here, will you present the longer one here? I hope you can see it here. Yeah, here it is. That's the longer one. That resembles the single bond. The smaller one, the smaller one here, we have different types. Okay, so yeah. So you can look into that, guys. Please look at your model kit and look at the smaller one. So here it is. That's the triple bond, the smaller one. I hope you can see it here. That's the smallest one. That's the triple bond. The medium one, that's the double bond. And the longest one, that's a single bond. And that's really true. Single bond are far away from each other. They have larger distance among themselves, the atoms. Here is moderate, and the triple bond is so close to each other. So therefore, it's very hard to break or to combust or to let them react with the triple bonds. Always, it's not that easy to let it, let it, decompose or whatever. So it's a very small bonding, means it's very tight. The medium one is double bond. The longer one is the triple bond. And I hope that's, I don't have I have here. That will represent what? The lone pair. This one in the model kit will represent the lone pair. So let's do this one here, and then every group will raise, after done, raise your hand. So I know that every group done at least the model. We'll do H2S. So I will do, the sulfur is larger. So, and I need something that has two equal sides. So I can take this one here. Okay. And okay, guys. And one single one. One is here. Unfortunately, I have only one. Can somebody bring me another box to show you this, the second one? So this one is not the way I hoped. Let me take another one. Yeah, thank you very much. Thank you. So guys, just hold on. I'm trying to show you that's how to get one that has three. Okay, here we are. We need to resemble the real true shape in space. And then another one here. Okay, guys, just hold on, guys. Okay, guys, here it is. Okay, guys, it's unfortunate, but I'm just showing you how does it look like. This is H2S. You have, this is the hydrogen, single bond, single bond. That's the hydrogen here, correct? I hope this. Here we have single bonds, guys. That's the hydrogen here. That's one of the lone pair here, the top. That's in the back here somewhere, another lone pair. So it will look like this here. So it will look like this. Hydrogen is the green atoms, lone pair, those those two lone pairs. Okay. And the blue one is your sulfur. So I need every group will show me that you have done this one here. So each group show me that you have done this. Come on, guys. Do this now. Come on, guys. Let's do this one here. Okay. So that's the molecule here. That's what we have here, guys. That's what we have here. So lone pair in the top and the back, or the down, the other side, and those are the hydrogens, the two hydrogens here, and the sulfur is in the middle. So, okay, guys. And when you do this one here, guys, may I have your attention? Make a picture, make an image of that, make a picture of that in your phone. And then underneath the Lewis dot structure, you have the structure from there. You put the underneath it your image. That's how I know that you have done it. You are not really cheating with time here. So make sure that if you don't have the image, then I will understand you did not do the real. Yes, make an image of it, take an image of it. Yes. What's that? Oh, how to do, the question is how to do the total valence electron. Somebody will help here, somebody will help. What are the valence how many valence electron does hydrogen have? Hydrogen, valence electron, number of the group. Hydrogen is 1A or 1. So hydrogen has 1. So you have two hydrogens, 2 multiplied by 1. That's 4. That's for hydrogen. So this is 2. How about sulfur? Sulfur is 1. Where is it? In 6A. 6A or 16. So 6A. So it will have how many? 6. Number of the group. So it will be how much is 6. 6 plus 2 makes out 8. Okay, guys? Good. I did not see that, but we'll do it together. So you know how to use the snipping tool? You know how to use snipping tool? When you go to the website, you snip the image, then snip it into this. Or image from your phone, upload it to your desktop or iPad or laptop, and then just squeeze it there here inside the Lewis. I need to see an image so you can understand how does it visualize, how does it look like. Yes. Unit, those are number. What is the units and region we say? How many we have for H2S? How many? 4. One single bond, the second single bond. The E, we treat them the same. That's 3. And another one E, 4. There are regions, zones, or we can call it whatever name is just to tell you, you treat the double bond, the single bond, the triple bond, the lone pair as such, as one unit or one region, or one group, one region, one unit, one group, correct? So did we do everything about this? Everything, we have everything about this. I need to see the image. If I don't, I'll take points. I don't really take points actually, but This one, I want you to take an image and then put it underneath here. So you can, you know how to, in the table, you know how to make it. You just go and make it bigger. What's that? Any question? Yes. No, for those, we have 5 only here. Hold on. Can I take this one out? So total VEs is 8. Total VEs is 8. So let me take this one out. So how many we have here, guys? 1, 2, 3, 4, 5, 6. That's all. 6 we have. And the other one is just post-lab questions. The other one is post-lab questions. So let's take the second one. HCF3. HCF3. So you can tell that the hydrogen always at the edge. Fluorine is the most electronegative, will be at the terminal far away, and the carbon will be in the middle. So we'll have something looking here. Look, guys. This is the carbon here, guys. This is fluorine. This is fluorine. This is fluorine. And this is hydrogen. Now the fluorine has 6 here. 7, I mean, with its. So this one here is, let's do it together here. So tell me what. So this is the Lewis dot structure. You can Google that. You don't have to draw it. You can Google it. You'll find it there, and you just snip it, the snipping tool, put it inside there, minimize the size of it, because when you go to the website, you'll see large image. So you can squeeze it and then you can minimize it there. So this is my A central atom. This is my B terminal. This is my B. This is my B. This is my B. Regardless if they are even different, but they are still terminals. They're called terminals. So the code is A, B what? 4. How many zones we have? Just look at this number here. 4. Now, how this 4 came from? Well, it is 1 single bond, 2, 3, and 4. 4 single bonds, 4 zones. Correct? So AB4, no lone pair. You go to the table there. This one will be tetra. What? Tetrahedral. So the angle is tetrahedral is 109 because that does not have, the angle is 109 because it does not have similar what? Terminals. We have 3 fluorine and 1 hydrogen. One is different, so that's nonpolar. If all of them fluorine, will be nonpolar. If all of them hydrogen, will be what? Nonpolar either. So AB4. This is tetrahedral. That's 109.5. It is polar or nonpolar? Nonpolar? Come on, give me a break. You can't tell me it. Look at the whole thing. Are all the B's are similar? No. So therefore, this is what? Polar, because they will be. They are not similar. The terminals are not similar, guys. Are you following me here? So now you tell me how to calculate the total valence electrons. Somebody will help me here? Somebody? 3F3. This one has 1, correct? Valence electron. Carbon 4A, or 4th group. Plus how many? 4. 6 is oxygen. Come on, guys. Look at the periodic table. Fluorine, how many? 3 multiplied by what? Where is it? 7A or 17. Multiplied by 7. So this is 1 plus 4 plus 21. How much is it? How much? 26. That's total VEs. Okay, so we covered everything about this. Now I need from you to Google this structure. If you don't find, for some reason, sometimes they are not, you just, what you will do, write it with your hand, like I'm doing here. Okay, take a snapshot of it, upload it, and then minimize it, and then add it to your, yeah. I have students, they don't like to just, they draw it with their hand easier, and then just make a picture of it with their phones, upload them in the laptop or desktop or iPad, and then just put it there. Now, what's the next we have to do? We are done with this? No. What we have to do? We have to look at the whole thing, correct? So let's make up a visual shape of this molecule, correct? So we have, it's a tetrahedral, correct? So tetrahedral, all of them are single bond, so you can see all of them are single bond, the same length, very tall. And now here you will see that this is the hydrogen, and you can see even that the size of this, guys, the size of this, that's a tetrahedral, guys. Look how nice is this. Is this nice? It is. I make a promotion for this model kit here. That's here. It's very nice, correct? Where is the hydrogen? Where is the hydrogen here, guys? Where is the hydrogen? In the top, because hydrogen is small. Atomic number is 1. Fluorine atomic number is what? How much is fluorine? Come on, guys. Fluorine is what? Fluorine, and then what will be? How much is the atomic number of fluorine? Look it up. Atomic number 9. Which will be bigger, 9 or 7? 9 is bigger. So that has to be represented here. Correct? So that has to be represented here. So this is the fluorine, this is the hydrogen. And that's how nice. Take a snapshot of this and upload it to your iPad or laptop or desktop. And then minimize it into the, where it said Lewis dot structure. Lewis dot structure will have a structure written or written by hand, or you Google it from the web, and underneath it, make space, underneath it will be this one. Okay, guys? Okay, so we have this one here. It's very nice. You can see it. This is very, very nice here. So now we are going to go over the third one. We're going through the third one. It's the time is still plenty. That's good. So any question about this? It is polar. And you know why polar? Because we have 3 fluorine, 1 different hydrogen. If all of them fluorine, that would be non-polar. If all of them hydrogen, that would be non-polar. So therefore, take this one out. Let's do the OBR2. Now, you tell me first about start from the beginning here. So let's see here. What is the total VEs here for this OBR? Oxygen is what? 6 atomic number. Bromine is atomic number is 7, and we have 2 bromine multiplied by 2. This is 14. So the sum will be what? 14 plus 6. How much? 6 plus 14 is 20. That's the total one. Okay. Now, your intuition will tell you, because now oxygen is 1 and you have 2 bromine, we can't put the bromine near each other. So we have no other choice, like H2O. We will put this time an exception for a rule we'll put the most electronegative in the middle and let bromine is electronegative as well, far from each other. So it would be looking like this. O, Br, Br, and then oxygen has 2 here. 1, 2, 1, 2. So this is the Lewis-Dot structure of OBR2. Okay, guys. So OBR. So now, how many zones we have? Somebody will tell me how many zones. Come on, guys. You can tell me. How many zones? 4. Correct. That's 4. Why 4? Let's count. I did not put the code on purpose, but I want to see if you can count them without the code. So this is 1 single bond, correct? You see here? 1, 2 single bonds. How many lone pairs? 2, 3, and 4. So this is A. This is B. This is B. This is E. This is E. So A, B2. E what? 2. Now, if you look at the code of this from the table, A, B2, B2 is what? Correct. I heard the correct answer is bent. And the angle will be around 105 degrees because you have 2 lone pair set, 1 and 2. So you can't count those 2 here. That will give you a number of zones. In this case, we have 2 single bonds and 2 lone pairs. And the angle is 105. Now, the question is, it is polar or non-polar? Non-polar or polar? Polar. Why? Because of the ease, the lone pairs. Blindly, if I have lone pairs, this molecule at the central atom, this molecule has to be polar. The same token here, if the opposite. Well, guys, I have to interrupt here. So sorry. I have to interrupt here. Stop.